When students have mastered adding one digit to two digits, they are ready to tackle problems involving two two-digit numbers. The most common strategy for these types of problems is partial sums. In this strategy, we add place value units, ones, tens, separately, and then combine these partial sums to obtain the sum. For example, consider the problem 44 plus 29. First, we add the tens. 40 plus 20 equals 60. This gives us our first partial sum. Then we add the ones. 4 plus 9 equals 13. This gives us our second partial sum. Now we combine our partial sums, 60 plus 13, to obtain the sum, 73. It is critically important for students to handle place value units correctly in both their work and their language. For example, a student may explain that they added 4 and 2 and got 6. We can point out the problem with this language by following through on the computation. 4 plus 2 equals 6. 4 plus 9 equals 13. And 6 plus 13 equals 19. However, 44 plus 29 clearly does not equal 19. We can help students understand the power of partial sums by giving them strings and sprints in which all of the sums have the same number of ones. In this sprint, all of the sums have 3 ones. This leads them to treat tens and ones separately and helps them to understand why this strategy simplifies the computation. A common error that students make with these types of strings and sprints is unitizing when it is not necessary or failing to unitize when it is necessary. For example, 40 plus 20 equals 60, and 4 plus 9 equals 13. We must unitize to make a 10 and add that 10 to 60 to get 73. However, in 52 plus 31, we do not need to unitize. 50 plus 30 equals 80. 2 plus 1 equals 3. So the answer is simply 83. Students may also make errors unitizing 100. For example, in 65 plus 38, 60 plus 30 equals 90. 5 plus 8 equals 13. When we unitize the 10, we now have 10 tens, and we must unitize them to make 100. As we know, unitizing is using digits to count groups of items as well as individual items, and we can help students develop their unitizing skills using the 10-frame place value mat. In this example, we have 9 tens and 2 ones in the 10-frame, and 4 loose tens and 7 loose ones. We are modeling the addition problem 92 plus 47. We can move all 7 ones into the 10-frame and still have an empty frame, so we do not need to unitize ones to create a 10. However, we only have one empty frame for a 10, so if we fill it, we must unitize the 10 tens to make 100. Now we can move the 3 remaining tens into the frame and see that we have 100, 3 tens, and 9 ones, or 139. In this example, we have 93 in the frame, and again we are adding 47. This time, when we add the 7 ones, we fill the 10 frame. Thus, we must unitize to make a 10. Now we have 10 tens, so we must unitize to make 100. We can move the 4 remaining tens into the frame and see that we have 100, 4 tens, and 0 ones, or 140. It is extremely advantageous if students can develop a metacognitive awareness of when they will need to unitize. This slide shows all the ways to obtain 3 ones when adding two two-digit numbers. Of course, the position of the ones can be reversed without affecting the sum. Thus, we can see that there are 1, 2, 3, 4 total ways to get 3 ones without regrouping, and there are 1, 2, 3, 4, 5, 6 total ways to get 3 ones with regrouping. We can see these patterns more easily if we look at a simple addition table for the digits 0 to 9. Here we can see the 1, 2, 3, 4 ways to obtain 3 ones without regrouping, and the 1, 2, 3, 4, 5, 6 ways to obtain 3 ones with regrouping. Notice that there is only one way to obtain 0 ones without regrouping, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9 ways to obtain 0 ones with regrouping. At the other extreme, there is no way to obtain 9 ones with regrouping, but there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways to obtain 9 ones without regrouping. Thus, we know that if a sum of two two-digit numbers has 0 ones, it must have involved regrouping unless we were adding tens. Similarly, if the sum of two two-digit numbers has 9 ones, then there could not have been regrouping. It is important to note that the number of ways to get any particular number of ones without regrouping and with regrouping always adds up to 10. When students understand this, they will be well on their way to a deep understanding of the base 10 number system. It is worth mentioning that some students may adapt the decomposition strategy from stage 13 when adding two-digit numbers to two-digit numbers. This involves extracting the tens from the second number and adding them to the first number. For example, 30 plus 40 equals 70, and 3 more equals 73. Or 52 plus 30 equals 82, and 1 more equals 83. In effect, these students create a 10-friendly equation which transforms adding two two-digit numbers into adding a two-digit number and a single-digit number. Thinking about addition of two two-digit numbers in terms of numeration provides many opportunities to deepen understanding of place value and the base 10 number system. However, students who have developed a strong mental number line will be able to use the strategy of compensation or keeping a constant sum to mentally add two two-digit numbers with very great efficiency. As we have already seen, we can use the commutative property of addition to find the nearest 10 and then use compensation to create a 10-friendly number sentence that's easy to solve. These two number lines model the addition problem 22 plus 47. First, let's find the nearest 10. 22 is a distance of 2 away from 20. 47 is a distance of 3 away from 50. Thus, we will use 20 to build a 10-friendly number sentence. If we subtract 2 from 22 to get 20, then we must use compensation to add 2 to 47. Thus, we can show that 22 plus 47 is the same as 20 plus 49, which is 69. In this example, we are modeling 23 plus 47. Both 23 and 47 are a distance of 3 away from the nearest 10. So whichever we use, we will get the number sentence 20 plus 50 equals 70. Now we are modeling 24 plus 47, and 47 is nearer to 50 than 24 is to 20. We will use 50 to build our 10-friendly number sentence. If we add 3 to 47 to make 50, we must subtract 3 from 24, which gives us 21. Thus, we have shown that 24 plus 47 is the same as 21 plus 50, which is 71. Finally, it is important for students to understand why we always choose the nearest 10. Let's look at the problem we just solved again, but this time let's use 20 to build our 10-friendly equation, even though it is not the nearest 10. We must subtract 4 from 24 to get 20. That means we must add 4 to 47. But notice that we cannot add 4 to 47 without crossing a decade, that is, without regrouping. Of course, we will still get the same answer. In this case, we are showing that 24 plus 47 is the same as 20 plus 51, which is also 71. However, we had to regroup in order to use compensation because we did not choose the nearest 10. By now, it should be apparent why compensation is such an incredibly powerful strategy for adding two two-digit numbers. If we use the nearest 10, we are guaranteed of being able to create a 10-friendly number sentence without having to unitize a 10. And 10-friendly number sentences are powerful because we can solve them without having to unitize a 10. This makes compensation the easiest and most efficient strategy for adding two two-digit numbers.